All right, welcome back to the Ethereum Protocol Fellowship Study Group. We are here today with our first session of the research track, here with Dankrad to talk about some sharding and some data availability sampling. So Mario, I'll go ahead and let you introduce Dankrad for us, and then you can take it away. If you have slides or a screen share, Dankrad, you can do that with the little present button down there.
Awesome. Welcome, Dankrad, and welcome all the attendees. So yeah, it's a tough task to give introduction for Dankrad because it's a man who mostly need no introduction. But I'll try anyway. So yeah, Dankrad is joining us today, who is a researcher in Ethereum Foundation, as you probably know. What you might not know is that he is also he has a background in theoretical physics from Cambridge, which is very impressive. And he's been doing great work on cryptography and Ethereum, most famously the Danksharding and the data availability sampling, but also MPC-friendly proof of custody, development of statelessness, and related protocols for maybe like 5 years now. So it's a really pleasure to have you here, Dankrad. It's an honor that you join our little study group, and that we will hear about the Danksharding from Dankrad himself. It's really great, man. So yeah, thank you so much for being here. Yeah, can you hear us well? Can you?
I can hear you. Yeah, thank you. The only thing is I can't see a button to present right now.
So in the under the video in the middle, and it's present. Right.
No, I don't have a present button. I have mic, cam, chat. I don't have present.
Oh, are you?
Is that maybe because I'm? Yeah, I am. Is that a problem?
You probably need a desktop to be able to share the screen. But if you share me your slides, I could.
Yeah, I'll do that. Yeah.
Put them on for you. Yeah.
Okay, I just sent him on Telegram.
Just give me a second, please. We can go on any moment. And yeah, just let me know if you need the next slide. I'll let you if you can.
Will do. Okay, perfect.
Can you move them or is it just...
Yeah, I can see them.
Okay, cool.
Cool. So move to the next one. Yeah. So just to what I'm talking about today. So I want to start from blockchain scalability to introduce why we have to care about data availability. I'll move on to the data availability problem. Talk about the solution in the form of data availability sampling, and then we'll be going more concretely into the Danksharding construction, and also talk a bit about the EIP 4844 that was implemented on Ethereum a couple of weeks ago. Next slide, please. So when we talk about blockchain scalability, so many years ago, Vitalik came up with the blockchain scalability trilemma. it says is that it is difficult to design a blockchain that provides scalability.
Dankrad just dropped, so just stand by. We're having a little bit of technical networking difficulties, so stand by.
Okay. Hello.
Hello. All right, that sounds better.
Is it better? Good. Okay, I changed my internet connection. Hopefully this will be better.
All right.
Sorry for that.
No
How
worries.
far were you able to hear me?
Last thing I heard was Vitalik came up with the scalability trilemma.
Right. So the scalability trilemma says that it's difficult to design a blockchain that provides scalability, security, and decentralization at the same time. And the important thing here is it doesn't say that it's impossible. Just back when Vitalik came up with this, we didn't really have all the constructions that were needed to make a scalable blockchain, but luckily we do have them now. And I'll talk today about one of the important components of the solution. If you can go to the next slide. So let's talk about like one of the parts here of the trilemma, which is decentralization. So when we talk about decentralization, what we mean is importantly, one important thing that we want is that it is pretty easy for anyone to run a node. And this is what makes decentralization difficult. So next slide. If we look at this node here, like ideally we want that someone can easily run a node in their own home. And this importantly means that two factors are limited. One is execution. This little box that anyone can buy for ideally at most a few $100 is limited in how much it can do. And also we want the user potentially to still be able to use it for other things at the same time. So we don't even want to use the CPU full time. And the second thing is the bandwidth. So like the internet connection that a person can get in their home is typically limited depending on the country. And so we have to be happy with like what we can get there, and that further limits how much one node can perform. Next slide. So if we look at the blockchain stack, it's like from our modern understanding, we see it as having like 4 different layers, and those layers are execution, settlement, data availability, and consensus. So consensus is basically how do we know which one is the chain that we all agree on? Like how do we come to agreement on what is the latest block? And that's like things like proof of work and proof of stake play a role here. Data availability is the part I'm talking about today, which is like how do we know that everything that was part of the blockchain is available to everyone? Settlement is the settlement layer, which means basically it's the root layer of all the, for example, assets on a chain. So it's kind of the logic that everything goes back to, and that tells you like, okay, this is who this ETH or ERC20 token belongs to right now. And execution is the layer that decides which transactions are valid. So execution is the layer that says like, if you execute this transaction, then the accounts change in this way, or they don't change because it was an invalid transaction. And if we go to next slide. So there are two of these layers are actually inherently like settlement and consensus. They do not really depend on the number of transactions that our blockchain has to process. Consensus does not depend on it, because consensus we can come to consensus on things like hashes. So we can very highly compress the amount of data that we have to come consensus on. So actually consensus doesn't really care if we have 1 transaction per second or a million. And for settlement, this is true in a similar way. We don't always need to settle every single transaction immediately. We can like basically net large numbers of transactions, and so settlement doesn't necessarily depend on the number of transactions either. But the two things that do absolutely depend on the number of transactions are data availability and execution. Data availability, because we need to have the data for every single transaction available to anyone who wants it, or at least anyone who needs it to know whether whatever they're depending on, for example, the balance of their account, is valid. And execution, similarly, like we need currently, for example, on Ethereum, to execute all the transactions, and so like it also requires to scale with the number of transactions. Next slide. And so a few years ago, we came up with the idea of so-called rollups, and this was finally, like previously there were many different ideas for scaling blockchains, like state channels, which are implemented on Bitcoin, for example, known as Lightning, Plasma, and others. But all of these have pretty severe limitations on what they can do, and they didn't really provide all the things that we want on Ethereum, especially like universal computation. But like with rollups, we finally came up with a way to universally scale computation. And they get their scalability from either using fraud proofs or validity proofs, also like colloquially known as ZK. And in this way, they can prove to all the nodes that transactions were valid without them actually having to verify every individual transaction. So that's where the scaling comes from. We need somehow to stop like every node having to execute all the transactions. Next slide. And then the final part of this is, how do we scale data availability? And that's what I'm going to talk about today. And the solution to that is data availability sampling. Okay, let's talk a bit about the data availability problem. So the definition of the data availability problem, it means that no network participant, and that includes a colluding supermajority of full nodes, has the ability to withhold data. So the important part is that this includes a colluding supermajority. So data availability is actually relatively easy to solve if, for example, you say like, oh, I'm willing to trust that the majority of Ethereum validators is always honest. And in that case, you could simply like make them all vote on it, and if they vote for it, then the data is available, and that is always true as long as they are honest. But that's not enough for like blockchains like Ethereum. We want the type of security that goes beyond just trusting a majority. We want that things like the validity of all transactions on the chain can be independently verified and have nothing to do with like whether the validators are honest. So the power of the validators in Ethereum is fairly limited, and this is an important property that we want to preserve. And this data availability is solved in current blockchains, including Ethereum, with like so far only one exception. or two exceptions, by all full nodes downloading all the data. So like current Ethereum nodes, they will always, whenever there's a new block, all the nodes receive the new block, and therefore they know the block is available because they've seen it. They've literally seen the whole block. And so the question is, how do we make this scalable? So scalable means that the work required should be less than downloading the full block. And more specifically, we want something like constant or maybe a logarithmic amount of work, like a square root tends to already be a lot. So like that's kind of our goal. Next slide. And so I like to like talk a bit more about data availability because like it's very often confused. So like data availability, what it does mean is that the assurance that the data was not withheld. So it's the assurance that the data was published. This is the important part. Next slide. What it does not mean, what is not data availability, is data storage. Data storage is 10 years later, you can ask, hey, what was the data then? This is a separate property that you can also want, but importantly, it's not data availability. So this is data storage or continued availability. And I'm not talking about that. This is also something you might want. Luckily, it's actually much easier to achieve that data availability. This does not require as like complicated constructions often, because as soon as the data is published, you only need one person in the world to preserve it. One person in the world is enough to always get that data. Whereas if the data wasn't published in the first place, then that honest person doesn't help you because they never received the data. So that's why data availability is so much harder to achieve than data storage. Okay, so this data availability problem, to many when they first hear about it, it like sounds like an unimportant detail. Like it's like just some annoying detail in many scaling solutions, like which we actually found many times. Like often, like people thought about, for example, Plasma, like was for a long time thought of being like the ultimate scaling solution, and in the end, it turned out it hit like big problems, and this was part of it, that it didn't have data availability. And so, why is it so important? So we have two options for getting fully scalable universal execution. And one of them is optimistic rollups, which use fraud proofs. So the way they work is you pause batches and make a claim that a new state root is the correct state root after executing the transaction. And after that, anyone can submit a fraud proof claiming that this is not the correct result. And then they play out a little game which has the property that whoever is right can always win the game if they play the correct strategy. And this is really cool. It only has one catch. What if whoever committed the fraud didn't publish the data? They just managed to somehow get the state root on chain, but without publishing the data. Well, now you have the problem that you cannot create the fraud proof because people might know, well, no, this can't be the correct result, but they can't prove it. So like, for example, like my example here is there could be like one tiny transaction there. It could be literally like, this is why you can't even miss a tiny bit of data. And it just like prints 1 trillion ether. And if you can't, you can't prove the fraud, then this would happen on the rollup. Obviously, this wouldn't really affect Ethereum itself because that would still be contained on that rollup. But like it would still be a huge problem for the rollup, and like everyone else would now not be able, like someone just can exit all this ether or however much the rollup had locked up, and like everyone else would not get anything. So we need really all data to be available unconditionally. Otherwise, fraud proofs cannot be constructed. For ZK rollups, it's like more subtle than that. Like for rollups, for optimistic rollups, it's really obvious why you need that. For ZK rollups, you could ask, well, I mean, even if the data is missing, nobody can ever really completely like make fraudulent transaction because you always have to prove correctness. But there is like this annoying thing, which is like basically, when you have money in your account, in order to access it, you need to prove that you have that money. And you cannot do that if you don't have the witness, or maybe you don't know how much money is exactly because someone made a dust transaction into your account. And basically, yes, your money is there, like nobody can steal it, so to speak, from your account, but they can kind of just lock it up there. And then they can blackmail you, obviously. They can say, well, I'll give you the witness, but you have to give me 50% of your money. So even for ZK rollups, where you can never have invalid transactions on chain, you actually need data availability. And this brings us to data availability sampling. So the idea behind data availability sampling is as follows. Here, instead of like we took our data here, and I've like basically chunked it up into these D0 to D9 little chunks. And the idea would be that what we want to do is, instead of downloading all the data, we just select some random bits of it and just download those. And we could hope that while if all of those that we request are available, then all the data is hopefully available. Right, but next slide, please. There's one little catch, which is that if any data is missing that we happen to not sample, we literally don't detect it. And the problem, as we discussed before, is that unfortunately, on blockchains, like even a tiny bit of data missing can be completely catastrophic, because we have this important financial information, and like, yeah, unfortunately, the missing transaction could be printing 1 trillion ether, and if we miss that, then we're just fucked. And so we cannot afford even one bit of data missing. And so this simple idea doesn't directly work. We can't just like split up the data into chunks. So here's an example. If we say like our client samples 10% of the data, like it's just quite a lot, right? Then the block producer could hide a single unavailable transaction. Now we know that catching this one transaction, the probability for that is 10%, because that's how much data we're sampling. But that's not a those aren't great odds. Just 10% of catching like an attacker who is trying to hide some important data, and we're already like sampling 10% of the data. So the trade-off here doesn't really work. So this brings us to the idea of erasure coding the data. So what we do instead is we don't just take the original data. So like here we have now 4 chunks of original data, D0 to D3. But instead we add some extra data to it. We like add a so-called erasure code. And in this example, it's specifically a read Solomon code. What that means is we take the original data, we interpret the data as points on a polynomial. And then we can extend it like this, like if we have 4 points on a polynomial, we know that we can always interpolate it into a unique polynomial of degree 3. And we evaluate that at 4 more points. These are E0 to E3. And now we have this really cool property of polynomials that says if you have any d+1 points of a degree d polynomial, you can always interpolate the polynomial, and it's unique. So this means that if I have D0, D3, E1, and E2, for example, then from that I can reconstruct it, and I will get back all the same points. And this is no matter which subset of points I take. Right. And so this is really cool, because now this original idea of sampling actually becomes efficient. So as an example, if we take 30 random chunks and all of those are available, then the probability that 50% of the data is unavailable is only 2 to the minus 30. That's 1 in a billion. So that's pretty low. So this is a huge difference to what we had before, right? We now just query 30 chunks, and that's a constant number. So it doesn't matter. It doesn't have to be 10% of the data. If we have 3,000 chunks, then it's 1% of the data. If we have 30,000 chunks, it's 0.1% of the data. So it's constant. And the probability is now really low. And we can make it lower. If we do 40, then we have 1 in a trillion. So it quickly becomes like an extremely low statistical event. But there's one catch to this, which is that quick correction. Does this work? This should say degree 3, not 5. But that's fine. So basically, what could happen is that these extension points were not computed correctly. That an attacker just makes up random points or whatever. And now what happens is that if you have any 50% of these points, you can interpolate it, but each of these interpolations will be different. And that's clearly bad because, I mean, the most important property of blockchains is always like that everyone agrees on the same thing. So we cannot afford this. And so we need a way of ensuring that whatever is in a block is always a correct Reed-Solomon code, or in other words, that the whole thing is a polynomial of the correct degree. And this is where we use something really cool, which is so-called KCG commitments, which are a type of polynomial commitments. And KCG commitments have the property that they always commit to a polynomial, and you can limit the degree of that polynomial. So you can say like, this root has to be a commitment to a polynomial of degree 3. And what this means is that we automatically get the property that whatever anyone, whether it's an honest node or an attacker, commits to is always a polynomial of the given degree. And so it's not possible anymore to commit to an invalid root. And this is like a really nice discovery that we made a few years ago, and that finally made it possible to implement. And luckily, it has become very efficient over the last few years. Cool. So let's go into the Danksharding construction that I came up with a little bit more than 2 years ago. So let's talk about what sharding originally looked like, or what many people imagined it as, what it would be like on Ethereum. So the idea was that so we always had like this beacon chain plus later like we added the execution blocks to that. And then the idea was that in parallel to that beacon chain, there would be many shards. Originally it was like 1024 different shards, all running in parallel. And similar to the beacon chain, each of them would have a proposer. And then each of them would have a committee that votes on whether that proposer showed up and what block they proposed. And so the question is, why was that necessary? Why do we need all these committees in here? Well, the problem is that each of these proposers can do something bad. Each can like not publish their data, or each of them can like publish 2 different blocks at the same time. And that has important consequences, because now the next problem is these committees can be split. Like, what if, sorry, state this at that, yeah. These committees could just be 50-50. And well, then you have a problem. Then how do you decide which one was the right one? And so this meant that essentially we have to wait for a long time for these committees to confirm. And like, it could take several epochs until you knew what each shard block does. And when you start going through that design, you notice that brings along with it like a lot of problems in practice. Like, for example, I mean, just to mention one of them, imagine you are a rollup and you want to publish your blocks, but they don't get confirmed. And Now, what are you going to do? Are you going to publish the next block? Are you going to republish it in case it doesn't get confirmed, and so on? So it's actually really difficult. And I think until the end, there wasn't really a way to really figure out how to actually use this in an efficient way. So what I said was, what if we like change the design such that we include, sorry, next slide now. We let one proposer create all these shards and the beacon block. And then we only have one big committee that checks for all of these, whether this is valid or not. And we can do that because when you have one proposer, then we can just look at all of them together. And the reason for that is that if they fail to publish the data for one of the shards, then we can just let the block fail. That's their responsibility. They fucked up. Whereas when you have many different proposers, you can't be that harsh because you can't punish the proposer for shard 1 if the proposer for shard 2 did something bad. But when you like aggregate the responsibility like that, then you can do it. And the important reason why we figured out we could do that is because in the process of researching MEV, we noticed that the ultimate equilibrium was something like that anyway. Like it was very likely that that blocks would be built quite centrally by some parties, and that our whole design would be around containing the problems with that anyway. So like maintaining censorship resistance and making sure that they were honest and so on. That was already on the roadmap anyway due to MEV. And so so it made sense to just say, well, like we can get rid of all this complexity of having all these many proposers because in reality it will be one anyway. And we just need to contain the potential centralization vectors that come from that. Right. And so this is like the extension of that. So basically what happens is that in the world of proposer builder separation, you would always come get a, sorry, we're still on the previous slide. You would always get first a proposer block where a proposer selects a builder. And that can be like just a small validator. They don't need a lot of hardware to compute that. But then the main block would be built by a builder who has more resources and is able to construct the beacon block and all the shard blocks at the same time. There's one more ingredient that's with the Danksharding design, and that is the idea of having a two-dimensional polynomial extension. And so the idea here is that we can we take the KZG commitments for the rows, and these are essentially the shards, or like I think in more modern speak we would say we would call them blobs, and each of them represents like a bit of data. But then, and it is extended as we discussed before. So each line will be essentially one polynomial with an extension. But what we do in addition, we also extend them on the vertical axis. So each cell here will be extended down as well. And the nice thing about KZG commitments is because they are linear, you can compute the additional KZG commitments just using polynomial extension as well. And doing this has some important advantages. So basically, the cool thing about that is that we can reconstruct the data if we have any 3/4 of this whole square. It doesn't matter which one, but we can also do it in a distributed way. And so we basically have two layers of validation here. And one is first, the validators will validate that the original, sorry, can you use the next slide? With the validators will validate that the builder has done their work correctly. And they can do that by just downloading, in this example, 2 rows and 2 columns. And if they do that, then if the block's unavailable, so less than 75% of the data is available, they can never get more than 1/16 of the validators voting for it. So 1/16 of the attestations, which means that the block will basically be reorged and ignored if it's not available. So as long as there's an honest majority, the validators would never vote for that block, which is always a good property to have. Although we do not want to rely on the honest majority, it's the first step that someone needs to get past. Next slide. What is like a nice additional property of that is that because each row and each column individually is a Reed-Solomon code or a polynomial, they can be individually reconstructed. So as soon as you have 50% of one row or one column, you can reconstruct that row or column. And so this can happen completely in a completely distributed way. There has to be no like super node or anything to reconstruct all the data. It can happen in a very distributed way. Next slide. And then the last step is obviously we want safety in the face of even a malicious majority. And so this works using data availability sampling. And what each full node will do is they will choose like 75 random samples in the square, and they will download them, and only if they find all of these samples will they say that this block passes. It's now 75 because we actually need 75% of the samples in order to reconstruct the data, which is higher than our 1D threshold. And so this again assures that it's available. The probability of an unavailable block passing is less than 2 to the minus 30. Cool. So let's quickly talk about how EIP 4844, which you hopefully have heard about, upgrade a couple of weeks ago, and Ethereum fits into this. So if we look at Ethereum's data availability rollup, so yesterday, as in before EIP 4844, rollups got data availability through call data, which was really expensive and really annoying. And since the 13th of March, we added blobs, and so far only 3 blobs to the blockchain that now rollups can use in order to like get cheaper data availability on Ethereum. And then in the future, we will further extend this, so there will probably like be some extensions to EIP 44 coming end of this year or maybe sometime next year. And then hopefully within the next 2 years or so, we will get full sharding with lots of data availability on Ethereum. So the EIP 4844 design is very simple. We added to each block some KZG commitments to data, and the actual data to these KZG commitments is the blob data, and that is just separately distributed on the network, which means we can be a little bit more efficient. It can work in parallel, but everyone still gets all the data. So it's not scalable yet. It's just like some efficiency improvements around distributing data, and in particular, it starts a new data market. So like the main thing is they are now priced independently from execution. It's a new gas type, which is cool because so far the rollups always had to compete with layer 1 transactions, and that unfortunately often made it very expensive because the price for those tended to be quite high, and gas had to be priced data has had to be priced in a very pessimistic way. And that meant that we were quite limited. And so you can see if you look at like L2 fees or something, now we have massively reduced the fees for rollups, which is like a great achievement. Blobs are never required to compute the state updates. So in order to like see what the latest state of the Ethereum chain is, you do not need the actual blob data. You only need that to know that they exist. And so the whole idea is that we design this so that we can make all our future upgrades quite easily. So in particular, we already use KCG commitments, and this means that we can directly upgrade this to use erasure coding. Like right now, we don't use erasure coding anyway, but it's like very easily possible to add this. So almost all the work that we need to do can be done without consensus changes. The only thing that really consensus needs to do in the future is like update the number of blobs that we can support. And so that's really nice because it really just decouples this, and basically we can start working on the whole networking and DAS and so on without having to like make lots of more upgrades to Ethereum. And the last cool thing is that rollups will not have to upgrade again to benefit. So like the interface to 4844 will stay completely the same through all the sharding upgrades. And so like if they start using blobs now, then hopefully a couple of years from now, they will have like massive data availability from full Danksharding. All right. Thank you. And yeah, let me know if you have any questions.
Awesome. Thank you so much, Dankrad. Amazing. Yeah, very well. Yeah, thank you so much for your talk. Really appreciate it. It was very insightful. I believe that we learned a lot. And folks, if you have any questions for Dankrad, please write them in the Discord thread, and we will ask shortly. Yeah, I wanted to ask. Yeah, there is a question. If you can elaborate a bit more about the current state, the current steps and challenges. So you mentioned there are some upgrades to be done on 4844, like the erasure coding and then the path to the full sharding. So yeah, what are the problems, the challenges being solved right now to achieve that?
So with 4844, I mean, there are some things we would like to do. I'm not like actually like fully like looking at these at the moment. I think like currently we're mainly seeing how it all works. I think there were like some very minor problems. But I think like mainly it's like the idea of watching it, and like over the next year, hopefully we can just like increase the number of blobs on there. I think when it comes to sharding, like there are definitely some pretty big hurdles that we still need to take. So full DAS is a departure from basically the networking model that currently all blockchains use. Currently, blockchains typically operate on broadcasting. Like basically, it's like everyone sees everything, all the messages on the network. And with DAS, we want a much thinner network. We want to be able to like have only a very small number of nodes store each sample. And that prevents a big challenge in the face of possible attacks and so on. So like the possible networking constructions, we do have a pretty good idea on how to get like a medium amount of scaling. There's a construction that we already worked on, which is called PIDAS. So if you scale it to the extent that pretty much all samples are still in your networking vicinity, as in like within one hop of your node, then you can like still be pretty safe, and everything kind of works as it does now. So that's pretty nice. So this will be our first step, and I think like the next step, going to full sharding, that's still somewhat of a bigger question. Well, I mean, it is quite achievable if you onboard another security assumption where you basically say, hey, I'm happy to trust that there will be some super nodes who like always keep all the samples, and as long as one of those super nodes is honest, everything will work fine. And I think that's a relatively okay assumption to make, but many people are not too comfortable with it. With that assumption, you can relatively easily work. That's what basically Celestia is doing. It works for them. I think once you go to like a fully distributed system in terms of DHT, there's still like actual research to be done at the moment.
Interesting. Thank you very much. Awesome. Yeah, there's a question about the 2D KZG, where the number 75% is coming from, whether it's like 50% of the data for polynomial reconstruction but multiplied by 2, or
No, it simply comes if you solve. So you want 75% of the samples to be available. So you need 0.75 to the power of n to be 2 to the minus 30, and then you get 75 roughly.
Right. Awesome. Cool. Yeah, folks, if you have more questions, please go ahead and ask. Are there any drawbacks of proto Danksharding from security perspective or protocol perspective? Any trade-offs that you think there are?
In terms of usage, in terms of like for the rollups, or
For the protocol, from like the security, like for example, there was a lot of chat about that there is issues with bandwidth. So
right. Yeah, I mean, bandwidth has increased, so this is true. It's actually still, I think it's an interesting issue because yeah, there were some other issues with Denkun where like there were some bugs in the client software that increased bandwidth for completely different reasons. So I think like a lot of validators saw a high bandwidth increase that actually is not caused by the blobs, but by the attestation aggregation gossip. Yeah, I mean, I think yes, it is a bandwidth increase. I think yeah, to an extent. Yeah, we need to figure out what we're comfortable with. I think yes, there will always be a trade-off where some people will say, well, this is now too much for me. I think I hope very soon we will have constructions that that will reduce the bandwidth a bit that you need. But there is also yeah, there are ways to reduce the networking itself. So there's lots of optimizations that can be done at the moment.
Cool. Thank you so much. Yeah, there's a question about the data availability sampling, specifically the mechanism for identifying whether the node is storing the data honestly and how they will be slashed. So if I assume there is some kind of challenge, but what if the node is, for example, offline and acting honestly? Just whether we have some mechanism for this, yeah.
Right. So no, you cannot slash nodes, right? So nodes are not bonded. So there's nothing really that you can do. So nodes can just store the data or not. You can, if it's one of your peers. So like that's one of the advantages if you have like a very local system, it's one of your peers, then you can downscore them. You can say like, if you don't have a sample that I think you're supposed to have, then you're not a great peer. So like I might downscore you, and if your score is too low, I'm going to disconnect from you. So this is a possibility for storage. So currently we don't really have any explicit storage mechanisms, and this is, by the way, not a change in Ethereum. This has always been the case. Like nobody guarantees that past Ethereum blocks are kept as storage. It just happens to be the default node implementation. We will in the future probably include a construction that is called a proof of custody. That basically means that validators at least have to store it for a while in order not to be slashed. This is a future upgrade. That's probably a few years from now because it's not the highest priority at the moment. This will not directly help with data availability sampling, like individual samples, because like you can't really, like, yes, Ethereum doesn't really want slashing conditions that are really short term. Like if you don't answer within 10 seconds, you get slashed. Like that's pretty anti-Ethereum. Like it doesn't really work because, like, for example, for validators, we want that you're able to run them from home. You can have a bad internet connection and so on. So all these things are pretty long term and aren't really like to do with, can I get my samples right now? So you really need, like, yeah, this is one of the difficult things that you really need to rely on honest nodes a lot, and that's what makes sampling itself difficult.
Awesome. Yeah, that's very interesting. I didn't realize that you can use DAS to like scoring your peers. That's can be very effective. Yeah, that's interesting. Cool. Yeah, folks, please feel free to ask more questions. We have some more time with Dankrad, so use the opportunity to pick his brain. Um, I would maybe ask something like more general outside of the even outside like the sharding. This very exciting topic, of course. Are there any other domains that you find interesting, exciting, which you've been working on recently? Maybe even outside of
Hmm.
Ethereum. Yeah.
Hmm. Right. I mean, inside Ethereum, I think like one of the big things that, yeah, like currently, I think a lot of people are thinking about is the economics. So it's like a pretty big topic. I think like everyone is trying to wrap their head around what staking could look like in the future. I think like yeah, like it doesn't seem ideal that all the stake is grabbed by liquid staking tokens, and so we're trying to figure out if there is any way in which that is not the case. Um, yeah, so like a lot of thoughts around that. Um, Otherwise, yeah, I mean, no, I don't have any like. I mean, much of my research at the moment is trying to get sharding implemented and working all around those.
Awesome. Maybe you kind of mentioned the staking there, and you had a bit on the staking maximalism, liquid staking maximalism.
Hmm.
Maybe if you can talk a bit about that.
Right. I mean, I think so. This was like something I posted on Twitter. I think sometime last year. It was really, I think, a very try to think very blue sky thinking, and I don't think it's a great idea. But the idea was that what I think, like especially in the Cosmos Solana ecosystems, a lot of people think of staking doesn't really like issuance to stakers is not really real issuance because everyone can stake. So you like essentially in the end it becomes just like everyone stakes and then everyone is rewarded for it. So it's like a complete zero sum game. And obviously like in all of these they are based on delegated proof of stake. And I mean, in a certain way, it is like an appealing thing to think like, oh, like maybe that solves all of our problems if we could just make delegation the primary way to stake. And uh, I try to think about that. I think like Vitalik first, like basically the end result is always like why, like what do we get out of it? Like why, how do these stakers help us? And it's not really clear. Like unfortunately, it's hard. In many of these cases, it feels like staking simply becomes just like a pure money game, and there's nothing actually in it for the protocol. So like, then why are we even doing it? So yeah, currently I don't completely know. Like I think like it is interesting to think about all these proposals. I'm not currently very strongly leaning in any direction. I think like what I mainly feel these days is that we need to just like keep staking more limited. I think the most dangerous scenario I see these days is like if the whole protocol becomes like if all ether is staked. I feel like that's very hard to reverse. Like we end up in a world where everyone is suddenly, yeah, literally a stakeholder, and so nobody wants their income reduced, and obviously that like influences people's decision making. All of Ethereum governance would now be about like, oh, how many percent am I making on this, and so on. And so like that seems like a pretty dangerous and dystopian world. So yeah, I think along those lines. But yeah, we don't have the solution yet, unfortunately.
Yeah, thank you. That's very interesting though. Yeah, thanks for sharing that. And yeah, maybe also on the topic of staking, what's your feeling on when a protocol has enough economic security?
Hmm. Right. I'm actually a minimalist on economic security. I don't believe that. I think honestly, between 1 and 10 billion or so is all the economic security you'll ever need. I think we have like way more than is necessary already. I don't think that an attacker, like this is basically the front door. Like I think like the front door, like acquiring enough stake to like do something bad to Ethereum is already like so secure that no attacker will try to attack it. If I had $1 billion, let's rather say yes, like assume that Ethereum's economic security was only in quotation marks $10 billion. Now, in order to attack, you realistically say would need, I don't know, let's say it's $3 billion or five, let's say it's 5 to get 1/3. So not really like that, but like let's say where this is not how I would use $5 billion to attack Ethereum for sure. Just in order to basically perform one double finalization. That seems, I do not think that the double finalization will do that much damage. And I believe also that there are other potential vectors that are much, much cheaper. Like think about like how many 0 days you can purchase for $4 or $5 million. So I think like, yeah, I think we are far beyond the point where we need more economic security.
That's really cool. Yeah, it's a really great point. That there are basically other bottlenecks when the economic security is growing. That's a great point there. Yeah, thank you so much. Okay.
I'm curious if you can elaborate a little bit on what it looks like in a world where all Ether is staked.
Right.
Like, what are the conditions that like bring this into being?
Right. So, right. So basically, I mean, the main thing is like to understand that we have to think about like what happens with liquid staking tokens, right? So people like originally people stake because like they want a certain amount of like they get a certain amount of reward for essentially two things, like they lock up their money as security, so they lock up Ether, which means they can't use it like immediately, and they have to like run and validate it or something. And so liquid staking, in a way, like gets rid of that to a certain extent. So you don't need to run your own validator anymore. You get a little bit less reward and someone else runs it. And that does a few things. So it gets rid of the capital bottleneck. So like, okay, the other thing it does, is that it allows you to get out immediately as long as there's enough liquidity. Well, and there's a third thing, like you can also, that's kind of a function of the liquidity as well. But yeah, you can also use it, like for example, in DeFi, you can lock it up to do other things and so on. And what can happen is like, at a certain point, if there is like enough liquidity in liquid staking tokens, they could become so attractive that the reward is almost irrelevant. Like let's say Lido staked Ether had all the same functions as Ethereum itself, and people literally on exchanges started trading like LS ETH instead of ETH, right? So sorry, Steve. And so what's the difference now? Well, the difference is that like Lido staked Ether still has like a yield compared to Ethereum. So it will always be like, if everything else is the same, it will always be more attractive. And that's then even true if the rewards go down to 1% or 0.5% or less. So there's a potential runaway scenario here where even with extremely low yields, they could basically eat up everything. And the only thing that Ether would still be used on would be like directly paying for gas. Like that's still true. Like you have to ultimately change to Ether in order to pay gas. But I mean, probably like a reserve of a few percent of that is enough, like as long as that's all allocated to DEXs where you can efficiently buy it exactly when you need it. So yeah, that's a scenario where it could be that like basically all ETH becomes staked. We're currently not there yet. We clearly like are not seeing the extreme like staking pressures that we saw last year. It stopped at some point. I think we're seeing a little bit more staking again, but we're still not in a runaway scenario. So people still want like something like 3 to 4% yield on their staked ETH. And that makes sense because right now the main liquid token is still Ether. Like if, for example, you're thinking about cashing out during the bull market, you probably would think about, okay, at some point I want Ether. And what if at that point staked Ether trades at a discount, then I would have to take that discount. That might not be worth the risk, right? So currently we're still not at a point where people take like would be happy with like a very small yield, like less than 1%. But I can see that it could eventually happen, and I think that's what we are quite scared of.
Awesome, thank you.
Yeah, thank you. Okay, if we can hold you for a minute longer, maybe a few more questions. There's one about what are the common misconceptions about sharding? What would be like some top misunderstanding that people often come up with? You would like to debunk?
So I think one fun thing is that sharding, or rather our modern version of sharding with data sharding with rollups, necessarily means that there will be no more composability. So one cool thing is that rollups, also back when we designed execution sharding, yes, like this was like one of the huge problems we had with sharding, where like, okay, like every shard is its own little ecosystem, and like moving between shards would be definitely not synchronous. But with rollups, the case is actually a bit different because you can design very big rollups. Like, I mean, Jesse from Base like posted the other day, they want to scale to 1 gigagas per second, which is amazing, which is exactly what rollups should do. And the cool thing is that it's okay for rollups to do that because they do not have to be as decentralized as the base layer, because they can be held accountable by the base layer. Like we can maintain their security and maintain their censorship resistance, even if they don't, if they are built correctly, like if their smart contracts have like forced transaction inclusion mechanisms, etc. So what is really cool is that within this rollup, you can have massive ecosystems that internally have full composability to some extent. If you are willing to like integrate with the base layer proposers, you can even have composability with the base layer on a ZK rollup.
Right. Awesome. Thank you. Okay, we have one question about more. So if you can give us some maybe more specific open R&D problems around the data availability sampling and data development in general, maybe something that people can learn about, start contributing to. Yeah, many eager contributors here.
Right. Yeah. Concretely, the biggest open question is how to build a robust distributed hash table, or DHT. So if anyone is interested in working on that, this is like one really interesting, really cool topic. So one of the big problems with DHTs is like traditionally peer-to-peer networks have no limitation on who can join as a node. And that is somewhat contained in like, I mean, I mentioned this before, that's for our usual blockchains like Ethereum, Bitcoin, everything is broadcast. And if you rely on that, the cool thing is that you only have to assume that you're connected to one honest node. And that's like a fairly acceptable assumption that people are relatively comfortable with. and that makes it pretty hard. Even though you have this like free joining mechanism, anyone can join. It's quite hard. You can potentially trick new nodes. It's very hard to like trick nodes that are already well connected in the network. And so the problem with DHTs is that their security assumptions are much harder, and they break down even with like relatively like minor fractions of malicious nodes, which we can't really like guarantee, because like an attacker could literally just add 1 million malicious nodes to the Ethereum network and we would have nothing we could do about it. So yeah, that's currently like a problem that we have. If people want to work on this, nobody has really found a great design yet that works in the face, like can work on similar assumptions as current P2P networks.
Oh, awesome. That's very interesting. Yeah, I hope some folks from the study group will look into that. And yeah, we are at 70-minute mark. I think like we can slowly be wrapping up. Josh, do we have any more questions?
Yeah, we have. I'm curious if execution sharding is something that is on the roadmap at some point, and how that will differ from the data sharding.
Yeah, I mean, I think nowadays I view execution sharding very differently. I think like a lot of things have changed in the landscape in the last 5 years. And I would say the way I see some form of execution sharding come back into Ethereum would be that we start increasing the the gas limit of the execution layer. And the way we do that is by putting the execution layer itself onto our data layer, and add like proving through a ZK EVM to it. And so what we would have would be like basically the base layer would itself kind of become like a rollup, in that like full nodes don't have to verify it anymore. And at that point, I think like we can get to a point where we can like start scaling it itself. It's probably not going to be as aggressive as rollups will. Like we will probably be a bit more conservative. But I can see that we can like get 100 or 1000x eventually out of the base layer as well.
Great.
And yeah, the cool thing is it will remain fully composable, because it's still just like one like logical shard.
Cool.
Okay,
Yeah,
well.
I think that's all the questions that I see in here.
Yeah, yeah. I think we are out of questions already, and we are at more than 70 minutes. So yeah, we used enough of your time, Dankrad. I know it's precious, and we really appreciate having you here. It's been an honor.
Yeah, it's been a pleasure. Yeah, thank you for having me. Yeah.
Thank you so much, Dankrad. Yeah, we appreciate having you in the study group. We learned a lot, and I hope some folks will write a great documentation on our wiki and start looking into the data availability sampling and the related problems. Yeah, awesome.
Yeah, would be great. Yeah, thank you.
Yeah,
Thanks.
thank you so much.
Bye.
Yeah, have a great day. Bye bye.
Yeah, you too. Bye.
Bye everyone, and we'll see you on Monday.
Cool. Yeah, see you on Monday for another development track course with Dragan, I believe. Looking at execution client deep dive.
Yes, we will see. We will have Dragan, the developer, the lead developer of Red, if I'm not wrong, explaining the architecture of Red, looking into the code base, and if anybody is interested in Rust, in execution clients, in Red specifically, this will be a great learning opportunity for you. Yeah, awesome. See you then.
Cool. Thank you, everybody. Bye.
Goodbye.